Almost every substance we encounter in the natural world is a complex, interwoven mixture. Since matter is rarely in its elemental form, nearly every industrial process and medical test begins with a necessary step, the physical act of unmixing. The difficulty lies in the microscopic scale of these mixtures, which are categorized by particle size. Solutions contain the smallest particles, evenly distributed. Colloids hold slightly larger, suspended particles, and suspensions consist of heavy clusters that eventually settle out of the liquid over time. Because we cannot manually pick these elements apart at the molecular level, we must exploit the specific physical properties of the particles to force them out of their blended state. Before we can choose a separation method, we must identify the mixture's internal structure. We observe how it interacts with light. When a focused beam strikes certain mixtures, the light scatters, a diagnostic phenomenon known as the Tyndall Effect. Particles in a true solution are under a single nanometer, too small to interrupt light. However, larger particles dispersed within a colloid act as microscopic mirrors, deflecting the light and making the beam's path visible to the naked eye. We see this microscopic interaction in the real world every night. At a sports stadium, the floodlights cut sharp, visible beams through the air because the light is bouncing off suspended dust and smoke particles trapped in the atmosphere. Identifying the particle size through this light test narrows our technical options. While true solutions require phase changes like evaporation to separate, the heavier particles in colloids and suspensions can be manipulated through mass-driven techniques like centrifugation or density-based settling. For liquids that refuse to mix, like oil and water, the simplest tool is a separating funnel. Natural gravity pulls the denser liquid to the bottom, where a tap allows it to be drained away while the lighter layer remains. This process relies entirely on a difference in mass. If two immiscible liquids possess the exact same density, gravity acts on them equally. Neither will settle, leaving them permanently dispersed throughout each other as tiny suspended droplets. When gravity is not strong enough to separate tight colloidal suspensions, like extracting plasma from blood or cream from milk, we apply artificial force. By spinning the mixture rapidly in a centrifuge, we magnify the gravitational pull, forcing the denser materials to pack tightly into the tip. By manipulating mechanical force, either through passive settling or high-speed rotation, we can force dense materials to surrender their purity. When liquids blend perfectly, we use thermal thresholds. If two liquids have boiling points at least 25 degrees Celsius apart, we use simple distillation, heating the mixture until the liquid with the lower boiling point vaporizes, then cooling that vapor back into a pure liquid in a separate vessel. This image shows the massive distillation towers of a refinery. Crude oil is a complex mixture, requiring a precise technique called fractional distillation. Inside, scientists maintain multiple temperature zones. As heated vapor rises, different components hit specific cooling points and condense at different heights. We can also use temperature to isolate specific solids. Sublimable substances, like camphor, bypass the liquid phase entirely when heated, turning directly into vapor. This allows the camphor to be captured and cooled back into a solid, leaving all non-sublimable impurities behind. Heat acts as a precision thermal scalpel, slicing mixtures apart based on the specific temperature at which they change state. In paper chromatography, we utilize the different speeds at which substances move through a medium. As a solvent travels up a strip of paper, it carries dissolved pigments with it. Because each molecule moves at a distinct rate, the different colors separate out into individual spots. Managing the total final volume is essential for precise concentrations. Creating a 50% mass by volume solution requires dissolving the solute first and then carefully adding the solvent until the resulting mixture reaches the exact 100 milliliter mark. This image illustrates the first stage of crystallization. By stirring a solid like copper sulfate into water over a burner, we utilize heat to increase the solvent's capacity to hold the dissolved solute. As the saturated solution cools, the water's capacity to hold salt decreases. The excess solute is forced out, interlocking to form pure geometric blue crystals. The end result, as shown on this watch glass, is pure copper sulfate. The solid has been completely isolated from any liquid impurities that remained in the solution. By controlling the specific rules of how substances dissolve and move, we can extract absolute purity from a chaotic chemical soup. These laboratory separation techniques support the infrastructure of modern life. They allow us to refine the fuel that powers our cities, analyze critical blood samples, and isolate targeted medicines from plant extracts. The universe favors complexity, naturally blending elements into interwoven and dispersed systems. By observing the hidden physical rules of density, boiling points, and solubility, scientists can override this natural tendency to mix. This mastery of physical properties gives us the ability to isolate specific, pure substances from even the most complex environmental or biological blends.